In this video, I will be demonstrating how to solve a potential difference problem. Uh, we have a infinite plane of charge, uh, rho of s, given on the 0 equals to 0 plane, and we have been asked to find the potential difference of moving our charge from this point to this point. So to tackle this problem, I will go through some three concepts real quick, and then we can come back to this problem and solve it. The first one that I would want to talk about is the infinite plane of charge. So let's suppose we have an infinite plane of charge. Uh, this is gonna be y. So we have an infinite plane of charge on our page, which is z equals to 0. And let's put a charge over here. Now, we know our electric field component will have an electric field component in the x, an electric field component in the y, and an electric field component in the z direction. So I'm gonna tell you that the electric field will not be dependent on the x or y direction, and let's see why. Now let's suppose I move this charge and I place it over here. This is our surface. So if I move it over here in the x direction, what do you see? We see there is no change because we have the same view. We have this uniform field of charge, and it's the same even if you move it over here or over here. The plane of charge below it looks the same. So the amount of force acting on the charge would be the same. The electric field lines coming would be the same. So our electric field will not be dependent in moving across the x axis. Now if I move this charge on the y axis, like I move it below or I move it on the top, you will see that now still we have the same view, or we have the same plane, and moving the charge in the y direction is not going to change our electric field. The electric field is still going to be the same. It's still going to be emitting in the same direction, and moving our charge will not do anything. So we know we have no x component, we have no y component, and we do not have any z component, and we can demonstrate that by that we our electric field is not dependent on the z component. Let's show that. So this is our z plane and this is our x plane. Let's suppose we have a positive sheet of charge over here. So we know we will have electric field going, because electric field emits from the positive charges in the radial direction. So we will have our electric field going on the top. These should be straight lines. I'm really bad at drawing, so okay, positive. This is going to be emitting over here. This is going to be emitting over here. This is going to be over here, and this is going to be emitting over here. So let's suppose I place my charge over here. So if I place my charge over here, we know it's gonna experience the force in this direction, and it's gonna move in this direction. My charge is gonna move in this direction, in the positive s of z direction. Now, what happens if I put my charge over here? It's the same thing. It's gonna feel it's gonna move in the same direction as that of electric field, because it's gonna feel the force from the electric field. So our Q goes from here to here, and that's gonna be our force. Now the magnitude of these forces will be the same. The only thing that's changing is the direction. Now this one is going at the positive z direction, so this is the positive force, and this over here is going at the negative direction of z. So we have a negative force over here. So only our signs are changing, but not our magnitude. It's going to experience the same amount of electric field. So our electric field is not dependent on either of these components. So let's suppose, well, now let's see, look at this. So we have this sheet of charge. Let's call it, we'll call it this rows of S. Rows of S. Now, rows of S is emitting electric field over here and the electric field over here. So that means our electric field is just going to be then let's talk about density, electric flux density. So electric flux density is just going to be our epsilon E times our electric field. So we know our electric field flux density from Gaussian's law. Gauss's law is d ds equals to rhos of v ds. Now, because our surfaces are the same, we can say that if we break this d down in the z direction, we have d of z and our some surface rhos of v on some surface. Now, because our surface is the same, these surfaces will cancel out, and we will have our electric flux density as rhos of v. So this is a very vague explanation, not a very good explanation, but to make this video short, I don't want to get into that, explaining into how we get the electric flux density being the same as rho of V. So let's look at this area. So we know over here this is going to be rhos of S, but our surface charge density, as you can see, is on the z equals to 0 plane. It's emitting electric field intensity, electric flux lines, flux density on the positive z-axis direction and in the negative z direction. So this area over here will give us rhos of S over 2, and this area over here would give us rhos S over 2, because it's emitting our flux lines in both directions. So this has to be half of in both the directions. When you add them up, you will gonna get rhos of S. So from here, let's look at what potential is. So if I place my charge over here, I know it's gonna feel a force in the same direction as my electric field. You can also look that from our formula of Coulomb's law for force. Force is charge times electric field intensity. So the direction of force will be the same as the direction of the electric field. Now, if I move my charge on the top, the force would be same. But moving the charge on the top will not require any work, because essentially the electric field component on the y, vertical component is not dependent on the electric field, as we talked below in the below figure. It's only in this direction, so its dependence is only on this axis, whatever this axis is. So what if I move my charge opposite to the direction of my force? Now, let's say that if there is a very strong wind coming from one direction to the other, if I'm walking the same direction of the direction as the wind, it would be easier. I would feel a force of the wind pushing me towards the same direction, right? So I can essentially walk, and the force will make me walk faster. Like I will be gaining kinetic energy. But if I go in the opposite direction of the field, I will have to force myself. I will have to put more energy into moving in the opposite direction. So moving from this point to this point will require work, right? Will require more work. So this is our definition of work when we are moving from one point to another in the opposite direction of the electric field, and that's how we get our equation. So the amount of work. Now, what is electric potential? This is the equation. So the electric potential is the potential difference from here to here. So this would be our P, this would be our P2, this would be our P. So the electric potential difference is, oops, okay. So the electric potential difference is is doing work on a 1 coulomb of charge moving from one point to the other in the opposite direction of the electric field. So this is what potential is. Now we already talked about how the electric field component will not depend on the y component, on this vertical component, because the electric field is acting on the horizontal component. So moving this charge from here to this point will require no work. So there will be no work done. The potential would be the same. Now real quick, I want to talk about what electric potential equipotential surfaces are. So here I have my charge, and I know it's emitting electric field intensity in the radial direction. So this is our E. I'll make these round circular surfaces around it. Now, because our electric field intensity is, is only dependent on the rho component. Like you can see, if this over here will have a change, is will our electric field intensity would be lower over here than compared to here, because our charge is closer over here. But if I put a charge over here, it's gonna experience the force in this direction. If I put a charge in here, it's gonna feel the charge is gonna feel the force in the rho direction as the same as the electric field intensity. Now, if the amount of force, because we know force is just Q times E, so we know the amount of E acting on this surface is going to be the same. It's going to be a rho. It's going to be, depending on our rho component, is going to be the same around this circle, right? The radius is going to be the same. So if you move a charge in this surface, it won't change. The potential difference is going to be zero, because over here we have our equation, force equals to QE, and we know our charge value is not changing, and our electric field intensity at all these points are the same, because the rho is same in all these directions. So moving a charge in these would have no potential difference. Similarly, moving over here would have no difference, but moving a point from here to here would have uh, uh, a work done, because we are moving in now from rho higher potential field to a lower potential to field. So basically, let's just keep our topic on the equipotential surfaces. That moving across this surface, the work done is zero. The change in potential is zero. Now oops, no, I don't know what that is. Let's look at our question one again. So we know we have a, on z equals to 0 plane is a surface charge density, okay, and it's a negative surface charge density, okay, and we are moving from 1 meter. Our point is our potential difference at this point, which is we 1 meter, 2 meter, negative 2 meter, to 2 meters, 3 meters to 4 meters. So let's draw it out. So let's say this is my z, and there is my surface charge, and this is my x. As we talked before, let's first draw these out. So we know that electric field always our electric flux density or electric field intensity always come out from the positive to the negative. So over here, the electric field lines or electric flux density would be pointing towards our plane, right? Okay, so this over here is our electric field intensity, or we can call this as our flux density over epsilon E. Over epsilon E. Yep, okay. So this over here is our, okay, so these electric field are pointing towards our, because we know it's going to be from positive to negative, so from somewhere our electric field lines are emitting and ending up at this negative charge. So let's say if I move my charge in the x direction, so where is it? X is 2. X is from 1 to 2, so I had over here 1, I had over here. So moving from here to here, you can see there is gonna be no work done, because essentially this is an equipotential surface, right? There is no force acting, because the electric field intensity over here and here is the same. It's not dependent on the x, like changing the x direction was not changing our electric field intensity. So that's going to be the same. Now, if we look at a similar argument for our y component, it's going to be the same because our electric field is only in the ace of z direction, only in the ace of z direction. So over here on the top we can see it's the negative ace of z direction, and over here in the bottom we can see it's on the positive ace of z direction. So what next? Okay, so we only care about the z-axis. We only care about this part. We only care about moving our charge. Let's suppose this is -2 from this point to this point. This is where our potential difference is going to be. So we have rows of s over here, which is rows of s. So this is rows of s. So the top part would be just the flux density, would just be our surface charge density halved, and the below part would be just our flux density over over 2. So here we are going in the negative ace of z direction. Over here we are going to the positive ace of z direction. So we put those in. So we know for z is bigger than 0, I have is the electric flux density is going to be rows of s in the negative direction. So let's put a negative sign first, negative, and I'm gonna put in the value for rho of s, which is -4, and we know that our epsilon is 10 to the -9 over 36 pi, so I can essentially substitute that in. So we have -4 epsilon over here in the ace of z direction. So our electric flux intensity is going to be, for density is going to be, oh, those divided by 2. So it's just going to be +2 in the ace of z direction. And similarly for z is less than 0, we have our electric flux density. Oh, I also forgot my. It's going to be negative on a -2 epsilon O in the ace of z direction. So we know our change in potential is V from 2, 3. Okay, I don't have a lot of space, so I'm not going to write all the components down. We know our potential difference is only dependent on our z component, so it's going to be from the z 4 meter to -2 meter, which is the work done to move 1 coulomb of charge, negative our integral of E dot dl. So we know that E is, or D is epsilon times electric field intensity. That means our E is uh, our electric flux density over epsilon of naught. So we can see if we substitute that back in, we can get our electric field over here, and which is d over E, and d is -2 epsilon of E. So our epsilon of E will cancel. So our electric field would just be -2 over here and +2 over here. Now solving this further, I'm gonna take this off so I have more space. Okay, let's. Okay, yep, let's zoom in. So this is gonna be negative. Let's break our integral down because we essentially have two different values, and so we are moving from -2 to 0 E dl plus minus 0 to 4 E of dl. So this is from here, right? We're moving from -2 to +4, yes. So this would actually give me, okay, so our dl over here is just going to be our dz because we are moving in the z, our differential length is just going to be dz because we are moving in the z direction. So I can write this as, what is my electricity from VR less than 0? It's -2. So negative negatives will cancel. I'm gonna have +2 times the integral of z, dz is just gonna be give me z, and I'm gonna evaluate z from -2 to 0, which is gonna give me 0 minus -2, a +2. +2, and that's okay. Yeah, that's all. And for here we are have negative. Same, we have dz. Integrating dz, we will have a z which we will evaluate from 4 to 0, top minus bottom. So 4 minus 0. So I have over here is, what is my E, electric field intensity for z is bigger than 0? It is positive 2. Is it positive? Yes, it's positive 2. So 2 times evaluating of this is gonna be positive 4. My electric field for z is less than 0 was -2, so I had -2, positive, and this, why did I write this is gonna be -2 because 0 minus 2 for is z. Oh, it's -2, so this should be plus. Okay, so we have this, and over here we have is 2 times 4. This just gives us 4 minus 8, which is -4. I think I made a mistake because this value should have been positive. So let's look at where did I make the mistake. My d over here above 4. Move this out. Okay, on the positive z scale I had was d equals to rho of s over 2, moving in the a sub z direction. We had the negative s sub z direction, so this was negative s sub z direction. Okay, yeah. So let's move on. This should have been a positive 4. I believe I've made a mistake somewhere over here, or either doing my integration, because it has to be positive. But I can later make another video and come back to this where I will just do the correct solution and post it. So let's see over here. So what is this? So over here we wanna see the potential difference from this point to this point. Over here we can see in this point. So we are not moving in our x direction, we are not changing our x directions, and we are not changing our z direction. We are only changing our y direction. So let's suppose I have this negative charge surface density, and this is my y. So I know my electric field is coming over here from positive to negative and positive to negative, and my charge movement is from here, from this point to this point, 4 meters, and y is over here is 2 meters. Now, as we had talked before, moving my charge from here to here is going to require no work done, because this is essentially an equipotential surfaces. So v of 2 4 positive 4 minus v2 2 4 is gonna give me 0, because there is no work done. The electric field is in the z direction only, and moving in the y direction uh, would not do anything, because the charge is going to feel the experience the same amount of force, so, and same amount of electric field intensity. So as we know, our for work done we have to go to the opposite, or at the direct in the opposite direction of our electric field intensity, and over here we are just shifting right to left. So this is our equipotential surface, and that's how we are changing potential is going to be 0, because the charges are not moving in the a sub z direction. Thank you.